Hi, today I'll be talking about this paper, an analysis of protein domain linkers, their classification and role in protein folding, published in 2003 by Richard E. George and Heringa. So the domain linkers can play an essential role in maintaining cooperative interdomain interactions. Not only is the composition of this linker important, but so is its length. In general, alternating the length of linkers connecting the domains affect protein stability, folding rates, and domain-domain orientation. In this paper, they took the non-redundant protein set available in NCBI and grouped them into similar sequences using single linkage clustering based on their BLAST p-values, which were lesser than 10 to the power minus 7. A final set of 1867 proteins was generated using the automatic Taylor method, which determines domains by their compactness in space. Similarly, for each protein, linker regions were determined by branching out from the domain boundaries assigned by the similar Taylor algorithm. The structural environment of each of these isolated domains were then studied by calculating their residue solvent accessibility. The linkers were divided into several sets based on their lengths and also classified by the number of linkers involved in connecting two domains. The linker propensity is described by a relation where PA is the propensity of the amino acid I, NRI in L is the number of amino acid type I in the linker set L, and the NRI in T is the number of amino acid type I present in the full protein set, respectively. Amino acid densities were then further calculated using this relation where PAB is the residue pair propensity to be found for a given peptide AB. PA and PB are the individual propensities calculated from this relation. So as shown in figure 1, the linkers were found to have an average length of approximately 10 residues, and the linkers were split into several sets as described in small, medium, and large linkers, with an average of 4.5, 9.1, and 21 residues respectively. The non-helical and the helical linker sets also exhibited similar length distributions to the full set. To study the linker conformation, the alpha carbon extent was also calculated. It was calculated by dividing the distance between two alpha carbon atoms with the number of residues minus 1. The average alpha carbon distance was found to be around 2.04 angstrom per residue. Overall, the largest population of linker residues, 38.3% adopt the alpha helical secondary structure, 13.6% are in the beta strands, and 8.4% are in turns, and the rest, 37.6%, are in coil or bend secondary structures. Further domain separation studies showed that more linker connections between two domains lead to greater hydrophobicity, less distance, and tighter interaction between domains, such that the movement between the domains are restricted. From this table, we can see the preferred amino acids in the linker sets were proline, arginine, phenylalanine, and so on in a decreasing order. Proline was likely to be favored in the data set because it has no amide hydrogen to donate in the hydrogen bonding, and therefore can structurally isolate the linker from the domains. The authors have also mentioned in this paper for interdomain that they created database for interdomain linker. Though the website seemed to have connectivity issues, the data shown in the paper can still be considered as a good resource for designing potential linkers for novel fusion proteins. Thank you.